You know, I feel terrible because this has been like the most awful week in Professor Land over like in the building a couple doors down, and so I'm like one of these terrible people that's coming in and giving a talk and leaving at a conference, which I hate. Like I despise people that do that. But anyway, I apologize, and I'm very excited that everybody's here and has the patience to listen to me today and share a little bit about some of the research going on. Of course, all of my students are doing the interesting stuff, and I'm just along for the ride. Right, I'm guessing this talk will be in a sort of same church, different pew from some of the things that you heard earlier today in the optimal transport area, which is great. It means that I don't have to do any of the hard work of setting up the math and can just show you nice pictures, which is always a fun thing to do since we come from computer graphics group in the CSAIL down the street. So one of the big themes that, I always come up with a different tagline for sort of what our group is up to. I can never decide what it should be. But as a person whose training is mostly in geometry and then somehow has been dragged into probability and statistics and learning, so somehow the way I've been thinking about a lot of the problems that our group has been studying is that there's somehow, trying to understand a geometry on the space of probability measures, which of course is exactly what optimal transport, as well as some of these other areas like information geometry and so on, are somehow after, right? And my path to this area was a little bit different from many of the people in this room in that, like, I originally came from a group studying triangles and meshes and rendering and PDE and all that good stuff. And of course, we're mostly concerned with points and triangles. And one of the things that we noticed is that when we take a lot of the really hard problems in sort of numerical PDE, geometry, and so on, and relax them, what you end up getting are probability measures as a result. And so from my perspective, it's just a nice sort of encoding of geometric features that we all know and love. And now we can go back to all of our favorite geometry problems and write them in this weird probabilistic way and see what happens. And of course, like a nice happy side benefit we kind of learned later, and of course now I tell our funding agencies is primarily what we work on, is that, of course, the same geometric reasoning we've been applying for years to points and lines and triangles and bunnies and teapots and things that we like in computer graphics are applicable to these sort of more high-dimensional abstract problems in statistical inference and so on. So when I step back and look at a lot of the machinery that we're developing in numerical optimal transport, machine learning, and so on, somehow the theme that I like to pull out is that we're sort of lifting geometric computation from the sort of classic, Euclidean Riemannian world into probability measures with the goal of being able to incorporate uncertainty, noise, and so on. Right? And so this appears all over the place, everywhere from the fact that maybe your data set is just some sampled version of a universe that you don't really have access to, or even something more concrete, like we work on, we have collaborators in LiDAR and autonomous driving where, when your car's driving down the street, you only get to see one half of the objects that are in front of you. And inferring a lot of information about the world that you can't see, of course, is a really critical problem in the computer vision domain. So at the most basic sort of level, when we ask about lifting geometry problems to probability measures, we have to take all of our favorite computations that we've done forever on sort of classical objects like points and lines and polygons and ask what sort of questions can we answer when we relax to this interesting encoding as like a point, as a delta measure, for example, and so on, into this more relaxed language, right? So there's a very classic example of this. Where if I have a shape in the plane and I want to measure its perimeter in the world's most complicated way possible, one way to do that would be to construct the indicator function of that shape. That's what I'm calling chi. So chi is 1 on the inside, 0 on the outside. And if I integrate the gradient of this function, of course this makes no sense in the strong version, but if I take this sort of weak version of this integral and integrate it along the plane, what I'll get is actually the perimeter of the shape, right? And so this is like a nice connection somehow between functional analysis and things that look like integrals and probability on the one hand, and geometry on the other. And this, of course, is a very classic idea that people have used basically forever in problems like image segmentation. And now perimeter is one thing, but of course one thing that we care quite a bit about is measuring distance. And again, the theme for today is taking like simple computations we do in Euclidean space and making them extremely complicated notationally. A different thing that we might want to do is measure the distance between 2 points. Right? So of course in probabilistic language, maybe a point is a delta measure at some location. Or here I've blurred it out, so now we have 2 Gaussians. And I might say, given 2 probability measures, I want to know, how far apart are they? In a way where when I measure distance and I take the red measure on the right and I move it even farther to the right, the distance scales like distance along the x-axis. And of course, if you compute things like L2 or KL divergence between Gaussian measures or God forbid, delta functions, and you just plot these things as a function of displacement of the red curve, This is my second talk today, and the last one was for 2 hours, so if I'm like falling over, I apologize. What you'll see is that they level off. They don't scale like distance. And so, of course, given the last two speakers on the program, I can only assume that you guys know the answer that I'm going to propose here, which is to use a machinery from optimal transport. In case you didn't like the I'm sure, extremely elegant formulations that these guys gave, let me give the one that I think about. So here's my front yard about a year ago. Fortunately, the city of Somerville it has a particular rule, which is that I can't. This was a work day. MIT is the worst. But in any event, this was all the snow in front of my house. And of course, before I could go to my office and teach everybody here, we had to move all the snow out of the way. As a lazy mathematician, there are many ways to do it, right? I could scoop up the snow and walk over to Philippe's house, which is apparently not too far away, and drop it down over there. Or I could do something more efficient, right? And of course, those are the amount of work that I put into moving that snow is largely a function of what? The weight of the snow, the back, how far I'm schlepping with this stuff, and so on. But no matter how hard I try to optimize, of course, there's a property of the snow itself, which is the amount of work it takes to get it out of the way, right? And that's some non-zero value. And in some sense, we can understand this as the transport or Wasserstein distance. Wasserstein, incidentally, he has very little to do with optimal transport theory, but it was sort of in the right place at the right time with his name. Literally is just about it. But in any event, the transport distance sort of says I have two configurations of snow on some geometric domain. And essentially what the transport distance is measuring is the minimum amount of work it takes to move from one configuration to another, where work is really measured as mass, like this d pi, times distance. And typically, in the transport distances, we allow our life to be a little more general, and we take that to pth power, right? So roughly when p equals 2, it's kind of like total kinetic energy, like 1/2 mv squared. And when p equals 1, it's kind of like work, right? Mass times distance. But I don't think I need to belabor this formula, because I'm guessing you've already seen them today. If I were a better colleague, I would have seen them myself in these talks. But are there any questions before I move on?
So the constraints are mu and nu instead of rho 1, rho 0, and rho 1?
Oh, have I already managed to use inconsistent notation? Oh, I have, yes. Yeah. So mu and nu are equal to rho 0 and rho 1, and this is what happens when you combine two talks in the middle of the night. Yeah. Okay, so there are basic transport problem, and we've heard a lot about the statistical aspects of this problem. A different thing that's worth focusing on and thinking about a bit is, of course, how to actually compute these numbers in practice. And there's many challenges associated to this, right? This is one of these problems where your input data is infinite dimensional, right? It's some probability measure. Your output data is even more infinite dimensional because it's a measure on the product space. And somehow, in a lot of applications, you don't even have access to mu, nu, rho 1, or rho 2, or whatever they are. But rather, you can only draw samples or have some noisy estimate and so on, right? So just as a numerical style optimization problem, this is really nasty stuff. And largely, arguably, that's why transport hasn't had quite as many inroads as we might like into the computational applied side, is because the expense of solving this problem is extremely high. Yeah, and of course, there's a lot of efforts going into reducing that, but it's still a lot higher than evaluating a formula. Okay, so this is an exciting opportunity for me as a PDE numerical guy. Great, you have some kind of continuum problem, some number you want. If only you could have an algorithm to compute it. So that's where our group comes in. And the really elegant and interesting thing, I think, about transport theory, other than all the cool statistical stuff you can do with it, it's just the sheer number of ways that you can interpret this basic formula involving scooping snow and dropping it back down that somehow look like they're viewed in totally different ways. We'll see that there's fluid dynamical interpretations and statistical interpretations and so on. And there's something that's very well known in the numerical PDE community, for people that are simulating fluids and liquids and solids and all that good stuff, that I think is worth thinking about here. That often there's a phrase that shows up in their universe. They say there's no free lunch, right? So the typical example here is discrete Laplace operators, right? Laplacian has a lot of different properties. It has a maximum principle. You can solve certain PDE with it and so on. And there's this very well-known theory that says every discrete Laplacian cannot satisfy all of the nice properties that the smooth ones can. That you kind of have to choose some subset of that list when you make your Laplace matrix. And that's why there's this huge cottage industry of people writing different discretizations of this operator. somehow I think there's probably something similar in optimal transport theory. There's all kinds of beautiful theory hiding here. We don't have a great understanding of how much of this we can conserve when we sort of transfer it to the computational regime. Right? So far, this has been a pretty ad hoc thing in the algorithms community. So the way I view it is it's sort of liberating in a sense. You get to choose your favorite theoretical formulation of this problem and your favorite discretization technique. And the art here, which hopefully we'll be able to turn into a science, is all about putting these things together so that you have an efficient algorithm and an accurate one for the application that you care about. OK, so today, I have a terrible habit of packing way too much stuff into talks. And I'm like running low on fumes. So we'll see how far we get in the 40 minutes and we'll call it. I thought I'd sort of use 3 very different starting points for where probability measures show up over in the computer science building down the street, and why you might want optimal transport in each of these applications. And then we'll follow those down the sort of computational rabbit hole and see that they'll end up in very different regimes computationally in terms of how to discretize and actually compute these things in practice. So hopefully that story makes some sense. In particular, we have sort of 3 tails. One is this teddy bear. He looks innocent, but he's got around 1,300 vertices. So there's 1,300 squared variables in your transport problem hiding on this guy. We'll talk about empirical, sampling style problems that show up in statistics, both from like a randomized perspective, as well as like I just have a fixed sample sitting somewhere in space, which are 2 slightly different scenarios, or some subset thereof. OK, so let's start by chatting about this histogram representation, which is probably the best understood one computationally in transport area. Undoubtedly, given the speakers earlier today, you've already heard about entropic regularization for transport, which adds a new objective term onto your usual optimization problem, which says that I'm going to promote the fuzziness of that matching matrix pi a little bit. And in exchange for that fuzziness, there are some really efficient algorithms for computing transport distance in practice. This is arguably the most impactful sort of idea in the applied transport universe, introduced, about 10 years ago to machine learning literature. And it really makes a lot of sense, right, for a lot of different reasons. It can promote certain statistical properties. And moreover, from my lazy applied perspective, many of these things are just models anyway. It's not that God told us that Wasserstein Distance is exactly the right thing to use for a given problem. It's just the thing that we know how to compute. And if that's really the case, then maybe regularizing is sort of OK. Right? Like, for instance, God didn't tell you the right way to interpolate between a tortoise and a cow, but you can get a pretty reasonable model out of transport, for what it matters. In any event, unfortunately, there are a lot of applications, especially in the domains that we care about in computer graphics, where entropic regularization really is not what we're looking for. So for instance, in the computer graphics domain, one of the main applications of transport stuff is to define different interpolation operators. So here, I'm thinking of a shape as kind of a measure on the plane. So black means probability, white means not probability, lack thereof, whatever. And now I can use, sort of averages in the transport sense to get nice averages of shapes. But of course, the input data here were nice sharp objects. And what's come out of this tool is not a sharp object, but rather a fuzzy one. And that's actually not predicted by transport theory. Transport theory tends to preserve sharpness of stuff when it's moving around. But rather, this is just a byproduct of the way that we regularize this problem. We added entropy to the problem. Yes, sir?
So you keep talking about shapes and probabilities.
Mm-hmm.
Are there conserved quantities?
Yeah. So for instance, the fact that these measures integrate to 1.
The amplitudes don't have to. It doesn't have to be conserved for shapes, right?
That's true. And certainly in these graphics applications, it's not clear. Like, there's not a canonical way to interpolate between shapes. There are statistical applications where that's not the case. But here, there's definitely a lot of wiggle room for modeling. I'm going to show you an application in a minute in numerical PDE, where these integrators really are used precisely for conserved quantities. So I'm going to put a pin in your question and return to it in 4 slides. OK. But in any event, I think what's clear is when you add a term that promotes entropy in your transport problem, what you get out is something fuzzy. And that makes perfect sense, because entropy is a measure of fuzziness. Yeah? And so for graphics applications, one of the questions that we set out to solve was how could we smoothly interpolate between measures on a surface where the interpolated objects don't have added entropy relative to the input data. And doing so is kind of fun from a numerical perspective, because it brings you in a totally different version of the optimal transport universe. So far, I've described the transport problem to all of y'all as a problem involving, matching two measures, and you can think about it like scooping up snow and dropping it back down. Let's shift our analogy a little bit, and we're going to use a different version of this story that was first introduced by Benamou and Brenier in 2000, which draws some ideas from fluid dynamics. So it turns out that the two Wasserstein distance, remember there's that p value floating in the formula before? When p equals 2, there's a really elegant reformulation of this problem, which is totally not obvious until you read the two-line proof, and you say, okay, fine. And it looks something like this, which is, let's say that I have two probability measures on some domain, like the surface of this teddy bear, or R3 turns out to be equally interesting. And I interpret these probability measures as the density of a gas at 2 points in time. Right, so that's going to be rho or mu or nu or whatever I chose here. Mu, sorry. And basically any Greek letter here other than pi is going to mean probability. Okay, then, right, one thing I could do is in 1 unit of time animate a motion of my gas from one pose into the other. And the really beautiful observation that Benamou and Brenier made, of course there are many different animations, right? My gas could spread out and then compact back onto the other pose or whatever. If you solve a variational problem that says, find me that animation in 1 unit of time that minimizes kinetic energy integrated over time, where that's just 1/2 mv squared, that number, that minimum kinetic energy, is precisely the two Wasserstein distance. And so what that leads to is a formulation of computing that W2 thing that looks an awful lot different than the linear program that we saw before. Right now, we have this time-varying density mu. And essentially, the constraint here is the continuity equation. This is saying that nu advects along a vector field that looks like m. Right? This is like what you would see if you were in a fluid dynamics talk. And your objective function here is, well, let's see here. So it's mv squared. And of course, if I change from velocity to momentum, right, then I get momentum squared divided by mass, right? And that's what you see in the objective. And the really beautiful observation by Benamou and Brenier is that this is actually a convex problem. Fun fact, x squared divided by y is a convex function as long as y is positive. And that's precisely what you see in the objective here, and the constraints are just linear. And so we use this as a starting point for discretizing the transport problem. And now rather than thinking of there matching different pairs of points in terms of moving mass around, we're solving a fluid dynamics problem and looking for the one with the minimum energy. And this allows you to invoke a whole different set of machinery from sort of numerical partial differential equation, right? Things that involve velocities and advection and so on. As usual, I'm talking too much, so I'll skip over the details of discretization. If you like this style of math, essentially it's things that involve meshes and triangles and so on. But the end point here is that you get a really beautiful preserved structure that you can sort of pull out of this Benamou-Brenier problem if you're really careful about it. Namely, the space of probability measures is in some sense an infinite dimensional manifold, right? So if we think of every probability measure as a point in some geometry, some extremely high dimensional geometric space, and then somehow optimal transport is giving me distances on that space. Then if you discretize this Benamou-Brenier formulation really, really carefully, what you get out is that essentially your discretized version of the problem is a geodesic on a manifold that's very, very carefully designed. So your metric sort of comes from the structure of this triangulated surface, and the space of distributions is just the set of things that add up to 1 on the vertices of the mesh. So it's kind of nice. You end up with just a finite analog of what happens in this infinite dimensional theory. So if you like playing with these kinds of things, we have code online. I noticed on my way in here that PowerPoint is broken and animations aren't working, but I can show you images of what it looks like. I'll catch you in just a moment. One really interesting empirical observation we made about entropically regularized transport is if you compute the sort of shortest path between two distributions with that regularization, there's an interesting phenomenon which I actually don't see explained in theory. Maybe our experts can help me out here, which is that what ends up happening is that the distribution kind of lingers on the two boundary data, and then it zips across the domain in a much shorter period of time, whereas what transport theory would predict is that you move with constant speed along the domain. I don't have a great explanation of why entropy would promote that, but the nice thing is that this other discretization doesn't have this particular issue. I saw a question here. Yeah?
Sorry, pardon the dumb question, but in the previous slide, you had this certain reformulation and discretization gives you a second order transport.
Mm-hmm.
So you see this is somewhat kind of higher in the hierarchy than LPs. So what is one gained? Is this a smaller program or something?
Oh no, computation, this is extremely expensive. This is, no, the difference is this is a completely different formulation of transport problem that preserves different structure. Like, so from a computation time perspective, this is quite difficult to solve. But from a adding entropy perspective, this doesn't happen in this particular technique. And moreover, it preserves this Riemannian structure. So for instance, entropically regularized transport is not a distance, right? It's a distance-ish object. But here, this is actually truly a distance on this finite dimensional space of distributions on vertices of a mesh. So it's more of a theoretical contribution than a numerical one. Although the types of numerical techniques you need to solve these problems are quite different, it's not clear that SOCP is actually so hard to solve. I know that in convex optimization, you always learn it later. But actually, these problems are pretty well conditioned. So oftentimes, it converges pretty quickly. Yes?
So prior to this, for example, there's a lot of variational methods on like diffeomorphic alignment,
Mm-hmm.
whole community of that.
Oh, yeah.
And so could we say that if they are conserving flows, like maybe non-divergent or things like that, that you could map that to this?
Yes and no. Yeah, so that community is really fascinating. The diffeomorphic registration people in medical imaging have really cool ideas. One headache they have is their problems are non-convex. Their objective functions are built from elasticity theory, and elasticity theory has this annoying property that compression and stretch behave very differently. So in some sense, these problems are much easier to study theoretically than what you see in that universe. In terms of conserved quantities, one thing that you can get from the theory of transport is that the vector field along which your mass is transported is actually divergence-free,
Right.
which is weird because fluid vector fields are curl-free. Or did I get that backward? I got that backward, I'm sorry. Fluid vector fields circulate, right? They have no divergence. These guys have 100% divergence and no curl. And so somehow, the intuition there is a little tricky to think about. So I don't know, it sounds like you're an expert. I would love to hear what you'd be interested in. In any event, the kinds of applications of this machinery are quite different from the sort of statistical world. For instance, there's a well-known sort of numerical integrator for PDE that's built on solving transport problems. It's called the JKO integrator. One of the nice things is that it actually does have conserved quantities in the sense that it is built on moving probability distributions around, so you don't have to worry about mass appearing and disappearing, which is often a problem in fluid flow universe. We've had the opportunity to play with this sort of Eulerian formulation of transport in a lot of different contexts, everything from political redistricting and understanding differences in partitions of a shape. And then recently I had a undergrad who took my class and built transport problems into his audio mixer, which really caught me by surprise, but has a cool DJ effect. Okay, so right, so now let's move on to something completely different, but really it's just a different representation of the same style of object, right? So over here, when we talk about probability measures, it's kind of like one value per vertex of a triangulated domain, and we're kind of interpolating that value linearly along the triangle faces. So it's just like a very classic numerical style technique. A different representation of a probability measure that's probably more comfortable in statistics world is just as an empirical distribution, right? So I put a delta function at every one of my points, I divide them by n, and of course that's itself a probability measure. Both of these are equally well suited to computation, right? Here it's one number per vertex, here it's a list of points. Yeah? You look like you're begging to ask a question. No? No? Okay. Right, so so here's our big formula. Of course, the space of measures that can be written this way is quite large, but not all measures. But in transport distance and many others, of course, you can approximate many measures in this form. I'm going to basically skip over all the nice theoretical properties because I'm sure that Ode and John have much more intelligent things to say about it than I do. But you know, of course, the sort of high-level 90 miles away point is that, of course, close to almost any measure under suitable assumptions and so on, a sampled, you know, distance between sampled measures and distance between the underlying things that you're sampling get pretty close to one another. But there's a gotcha. The transport problem itself is convex when you think about it in a function of measures. If you think about it as a function of the support points, like I want to find, you know, looking at the distance between two measures as a function of where I move those points in the empirical measures, that is not a convex function. right? So I can weight them up and down. It's convex in the weights. It's not convex in the geometry. And so some of the numerical techniques in this area are a little less trustworthy in the like global optimum sense because they look an awful lot like k-means, which is of course an algorithm that people have struggled to say stuff theoretically about for a long time. Right, so there are many different formulations of transport that look extremely different from fluid dynamics. That much is for sure when it comes to discrete regime. A lot of the ideas in this space involve a very simple sort of observation, which, you know, when you read the transport textbook, at least for me, I totally missed it, and then you kind of think for 5 minutes, and think, oh, okay, that's not so bad. So in one dimension, maybe I'll make use of this little inch here. Oh, there's inner products. That's nice. So let's say that I'm doing transport between some measure consisting of a finite set of points, whatever they are, and then some other measure that I can't say anything about. Maybe it's smooth and then like has a delta hanging out over there, like whatever. And I look at the transport map from one into the other. Does that make sense? There's a very simple argument that you can make, which is if I look, so this is an infinite dimensional problem, right? Because I have to figure out for every single point in this smooth distribution what its source point was in the other guy. However, there's a simple observation you can make, right? Which is the following. Let's say that I look at all the points in the smooth distribution which get mapped to the first delta function, like the leftmost guy, right? Then I think we can all agree that there's never a reason for mass to kind of leapfrog when you map from one into the other. So in other words, what can I do? I can sort all of these delta functions from left to right, and then I can just find locations where I chop the smooth distribution, and that's going to give you my transport map. So actually, even though it looks like there's an infinite dimensional problem, that's not the case, because really the variables here are just sort of the walls between the different parts of the distribution that I cluster together and map to these empirical pieces. Now this one-dimensional argument is very easy for me to draw on the board. It lifts to higher dimensions, and it gives pictures that are not particularly enlightening, but nice to look at. But essentially, you can think about this little diagram I've drawn here as kind of like a Voronoi diagram, right? It's like roughly the stuff closest to the first point, the second, and so on, but with a bit of a twist, which is that I have to balance the different cells of the diagram to integrate to the same value on the other measure. And the object that does that is something called a power diagram. And it's basically kind of like a Voronoi diagram where I bias the distance function up and down. And the cells associated to each of the points are called Laguerre cells. The nice thing is that actually computing these things is the thing we can do stochastically. And so we had a lot of different sort of previous work on exactly that, like computing, sort of approximating transport distances and derived things like barycenters by just sampling from one measure and then having the other measure being assumed to have finite support so this kind of picture holds. Right. So I thought for fun, again, in the theme of packing too much into one talk, I'm watching the clock here to make sure I don't go over. I'd show you guys two quick applications of what this kind of machinery can give you, which is going to look an awful lot different than the fluid dynamics kind of ideas I was showing you before. So for one, and both of these were at the NeurIPS conference a couple months ago, 1 month ago. So here's one from a friend in Bayesian inference. I'm not a Bayesian person. I feel like it's very easy to put your foot in it in that community when it comes to choosing the right language, but I'll try. So let's say that I'm trying to infer a parameterized distribution from a set of data, and I'm going to do it in a Bayesian fashion. My understanding of how you would go about that is I observe my data set, and now what I get back is a probability distribution over the parameters of my model. Does that make sense? So the example that we'll have here is, let's say I want a mixture of 1, 2, 3 Gaussians. Yeah, and so those 3 Gaussians are defined by 3 means and 3 standard deviations. And now I observe data, and what I get back is a distribution over like 6 numbers, right? Mean 1, standard deviation 1, mean 2, standard deviation 2, mean 3, standard deviation 3. So there's a bit of a problem that shows up, specifically in this kind of a setting, which is the following. Is there anything special about being mean 1? No. In particular, if I swapped mean 1 and mean 2, and their corresponding deviations, I get exactly the same probability value. Does that make sense? Because there's nothing about the ordering here that shows up in the Bayesian formulation. So more generally, there's a symmetry group that's acting on my posterior likelihood function p, right? Any permutation that I apply to the variables here doesn't affect the likelihood value. However, what happens if I take the expectation of this distribution? Well, now every point is equally likely to every other point in its orbit, so I kind of get just something blurred out in the center, right? So taking expectations here really doesn't make any sense until I quotient out that symmetry. And so this problem, which is one of those problems you look at and you say, like, somebody's like probably solved this in the 1920s, is known as label switching, and shows up in a lot of these sort of unsupervised models where you have like multiple explanations and they can swap out and they don't have a number associated to them. For fun, we set out to see if we could use transport to sort of address this and come up with a version of like what does it mean to compute some expectation-like quantity after quotienting by these sorts of symmetry relationships. And so the algorithm that we came up with, which initially looks really, really ugly, but turns out to be actually not that expensive computationally, is as follows. So here's our basic ambiguity, right? So I draw a sample from my posterior distribution. I could take its whole orbit under some group, and really all these samples are equally likely, and so it's not clear how to match them together when I compute expectation. So what we did instead is we said, I'm going to draw samples from my posterior distribution, take their orbit under this symmetry group, which has to be known. This is not like cryo-EM or something where you don't know your symmetry group. And now, if you think about it, it's kind of yucky. What it means is when instead of drawing a sample from my posterior, I'm really drawing probability distributions. Right? Because what I'm doing is I draw a single mu, set of mu's and sigmas, and I take their orbit, so I take every possible permutation, I combine those all together into an empirical measure with n factorial points. Initially, this sounds really messy computationally. And now I'm going to take the average of all of these guys in the transport distance. Right? And so there's a nice little lemma that you can prove that if you take the barycenter of measures that are all the orbit under some group, the thing that you will get back is itself the orbit of a point under a group, under some assumptions. Which is exactly what you want, right? Because that means that you kind of extracted a well-defined notion of mean without having to like choose a canonical way to permute the means and standard deviations, which is pretty nice. Now, computationally, that sounds really ugly, right? I'd have to like, it wouldn't scale very well, the number of means and standard deviations. It looks like factorial. Thankfully, there's a way to write down the entire sort of semi-discrete algorithm I described for you before in just one of the cells of that quotient space. So really you're just moving one point around instead of the whole orbit. And secretly in the back of your head, you're solving a transport problem just with lots and lots of symmetry kind of built into it. So this was a nice sort of application of this empirical style of reasoning, and it really depends strongly on the fact that our measures are constructed out of isolated points in a finite set that we kind of can say something about its structure. For a similar kind of more experimental application with less theory attached to it, our colleagues at IBM who are interested in natural language processing set out to apply some of this stuff to document retrieval and classification. And so their basic starting point was as follows. So this is kind of strangely high impact paper from 2015. It's like one of those ones you look at and you think like, I could have done that, man. But they get the credit, that's fine. On something called the word mover distance. So there's a very popular tool that in deep learning universe that takes words in the dictionary and embeds them as points in Euclidean space. How, you might ask? I don't know. Go read that stuff. But if you take a document, a document when I read a document for sure, it's just a collection of words. And so from that perspective, it's just some point cloud sitting in Euclidean space, which is of course an empirical measure. And now we're in business. We can do optimal transport on these things to do things like retrieval, right? You can see roughly when this paper was written based on the word cloud that they chose. But in any event, of course, documents aren't just collections of words. They're really collections of topics. But this algorithm is quite expensive because it scales in the number of words in your document. So it's good for like little blurbs on news sites, not so great for like textbooks. So what we did with our friends at IBM is incorporated some new some quite old ideas in topic modeling. So in that universe, you take a whole corpus of documents, and then what they do is they sort of infer things that you can think of as topics, which are just collections of words, right? So like I have a whole, I take the whole dictionary, and now I infer that like often animal words kind of occur together, so I'll call that a topic, right? So from this perspective, a topic is a collection of words. And also when you do this kind of topic modeling, you get that a document is a collection of topics. So this is some kind of hierarchical transport problem, right? A document is a distribution over topics. A topic is a distribution over words. And now you can do transport where your ground distance in transport is itself a transport distance. which is all kinds of messy, but actually computationally is much less expensive because the number of topics tends to be far less than the number of words in the dictionary, right? So one thing we can do is pre-compute the distances between the topics that are inferred by LDA, or whatever your favorite topic modeling tool is. That becomes just some small cost matrix, and now your document retrieval problem is relatively efficient. The kind of surprising thing to us is that not only was it more efficient, it actually outperforms the sort of basic word mover distance model in a lot of cases. And moreover, it's interpretable, right? Because now your topics are somehow collections of words. You get this transport map, which is telling you sort of why you think this topic is related to this other one. Our student Sebastian, who is the sort of main author on this work and a philosophical literature kind of guy, I think spent a lot of time designing figures in this paper, you know, basically kind of likes the judgment that it made about why different topics are related to one another. But in any event, it's some first step toward interpretability of some of these retrieval models. Now, exactly these kind of empirical transport ideas are applicable in lots of different domains, and I can point you toward other ideas. Essentially exactly the same. We're very lucky here. We have like kind of one hammer and many nails. We've managed to apply this in some embedding style learning problems. And then in a completely different domain, interpolation between vector fields on two-dimensional surfaces turns out to have a nice conserved quantity thanks to the Hopf-Poincare theorem. And so you can actually use empirical optimal transport to move around singular points in vector fields, which is a pretty surprising application of this stuff. So as usual, I think I've probably talked too much and should leave some time for questions. So maybe I'll skip the last little topic here. But I can point you to just a little bit of interesting work. So far, we've sort of restricted ourselves to relatively small subsets of the space of measures, right? Like things like empirical distributions or measures that can be written in terms of these hat functions on a triangle mesh. You can also ask questions about the whole space all at once, right? So for instance, given a measure mu naught, what does the space of measures look like in some radius r of mu naught in the transport distance, right? Maybe some of them are Gaussian, maybe some are empirical, like just a whole giant ball in this space. And this idea turns out to be quite critical for applications in distributionally robust learning, where maybe mu naught is like the data that I observe for some learning problem. But of course, when I run, I deploy my learning system in the wild, I'd like to shield against data distributions that are somehow similar. And so it turns out that transport distance has a lot to say about this area as well. We've worked quite a bit, I'll just draw, in distributionally robust learning where your adversary is allowed to be in some Wasserstein ball. It turns out that some of the previous models for this problem are really interesting theoretically, but have a kind of bad property, which is this is no confidence, and 0 is the radius that you actually would need for your problem, and you can see that unfortunately many of these models degrade before that point. By incorporating some unlabeled data into these models, it turns out that you can do much better, and I'm happy to provide you pointers to that work or discuss it offline. So maybe with that, I'll skip over all this stuff and just give you the main takeaway here, which is that, at least from my perspective as a geometry guy who's very tentatively stepping into the statistics and kind of learning area, from my perspective, measures give a really powerful language for kind of understanding and using the language of geometry and optimization to sort of think about both low and high dimensional problems. And of course, the really critical decision when it comes to computation is representation, right? That like what you would do on a triangulated domain where you care about graphics applications is quite different from what you would do in statistics or inference. And somehow, even though we have the same starting point, like just one value you want to compute, like the Wasserstein distance, it brings you to very different places. And it'll be interesting, I don't know, over the long term, whether just one thing will emerge as the key tool or not, but I suspect the answer is no, that there really is no free lunch and that there's an interesting theory to be developed here. So with that, I'm happy to take any questions you have. I can hang out for a little while, or I don't know what the usual structure is, but I appreciate your time and patience with my enthusiasm here, and thank you very much.